Reality might be nothing but a beautiful illusion. The physicist Niels Bohr once said the opposite of a profound truth is often another profound truth. This idea lies at the heart of 25 cosmic paradoxes that challenge everything we thought we knew. By the end of this journey, you will see the universe through a completely new lens, one where the rules of space and time are not what they seem. We will explore how a cat can be both alive and dead, and why the overwhelming silence of the cosmos might be the most terrifying answer of all. These are not just intellectual puzzles. They are the very contradictions that forced science to evolve, unraveling the fabric of our reality. Are you ready to question the nature of existence itself? A scientist in a laboratory aims a precise instrument at a single particle, hoping to pinpoint its exact location. Yet the very light used to see this tiny object pushes it in a different direction. The act of looking has irrevocably changed the thing being seen. This is not a limitation of our technology. It is a fundamental property of the universe, a phenomenon known as the observer effect. At the quantum level, particles do not possess definite properties like position or momentum until the moment they are measured. Before observation, they exist in a blurred state of superposition, a ghostly haze of all possible states at once. This leads us to one of the most profound questions in all of science. Does reality require a conscious mind to bring it into being? The classic double-slit experiment demonstrates this bizarre behavior with startling clarity. When particles, such as electrons, are fired one by one at a barrier with two slits, they do not simply go through one hole or the other. They behave as waves, passing through both slits simultaneously and creating an interference pattern on the detector screen behind, a telltale signature of wave behavior. But the moment scientists place a measuring device to determine which slit each electron actually goes through, the pattern vanishes. The electrons, as if aware they are being watched, abruptly begin acting like discrete particles traveling through a single slit. The wave of possibilities collapses into a single, concrete fact. This paradox forced physicists like Niels Bohr and Werner Heisenberg to develop the Copenhagen interpretation. It proposes that a particle's wave function, which describes its range of possibilities, collapses into a single reality only upon measurement. But what constitutes a measurement? Is it the photographic plate, or is it the conscious awareness of the scientist viewing the results? Theorist John Wheeler took this idea even further, suggesting we live in a participatory universe. In this view, we are not merely passive spectators on a cosmic stage. We are active participants, co-creating reality through the act of observation itself. This reframes the old philosophical riddle. If a tree falls in a forest and no one is around to hear it, does it make a sound? Quantum mechanics might answer that without an observer, the tree itself exists in a state of indefinite possibility, not as a solid, falling object. The sound and the fall only become real when a conscious mind is present to witness it. This places our awareness at the very center of existence, a staggering responsibility that challenges the objective world we thought we inhabited. And if our observation defines reality, what happens when we are not looking? The answer leads to a paradox even more bewildering, where a single thought could determine life or death for a cat. Yet this strange dance of observer and observed unfolds in the quiet of a laboratory. When we step back and gaze at the cosmos, we are met with a silence far more profound. The universe is unimaginably vast and ancient, filled with hundreds of billions of galaxies, each with hundreds of billions of stars. With so many worlds, the probability that life, even intelligent life, has arisen elsewhere seems almost a certainty. And yet, when we point our most powerful telescopes and radio dishes at the heavens, we hear nothing but an eerie, unbroken quiet. This is the Fermi Paradox, a contradiction so stark it was captured in a single, blunt question from physicist Enrico Fermi over lunch one day. Where is everybody? He reasoned that if intelligent life were common, a civilization only slightly more advanced than ours should have spread across the galaxy by now. Their artifacts, their signals, their very presence should be unmistakable, but the sky is silent. To grapple with this, scientists developed the Drake equation. It is not a strict formula with one answer, but a way to frame the question. It multiplies a series of factors like the rate of star formation, the fraction of stars with planets, the number of planets that could support life, and the fraction where life actually emerges and develops intelligence. The final, most haunting variable is the average length of time such a civilization releases detectable signals into space. Plug in optimistic numbers, and the galaxy should be buzzing with conversation. But the silence forces us to consider that one or more of these factors is tragically small. This is where the chilling concept of the Great Filter arises. It suggests that there is some immense barrier, an evolutionary or technological wall that almost no civilization can overcome. Perhaps the filter is behind us, a step in the development of life so improbable that we are a breathtaking fluke, truly alone in the cosmos. Or, more frighteningly, the filter might lie ahead of us. It could be that the development of advanced technology, like artificial intelligence or powerful weapons, inevitably leads to a civilization's self-destruction. The silence, then, is a graveyard. Other explanations are less grim but equally mind-bending. Perhaps intelligent life is common, but it evolves into forms beyond our recognition or communication. Maybe they are out there, but they have chosen to remain hidden, observing us like we might observe animals in a nature preserve, careful not to interfere. Or the vast distances of space and time simply mean that signals have not reached us yet or passed by long ago. This cosmic silence forces a deep introspection. Are we a lonely miracle, the universe becoming conscious of itself for the first time? Or are we a young, naive species, blissfully unaware of the dangers that have silenced every other voice that came before? The answer reshapes our understanding of our own future, and it pulls us toward even stranger mysteries where time itself may not flow in the way we believe. This cosmic silence stretches across the void, but the strangeness does not end there. It reaches into the very fabric of time itself. Take two identical twins. One remains on Earth, living a normal life. The other boards a spacecraft and journeys to a distant star at a speed close to the velocity of light. Upon returning to Earth, the traveling twin steps out of the ship, appearing only a few years older. They are greeted by their sibling, who is now an elderly person. This is the twin paradox, a famous thought experiment that arises directly from Einstein's theory of relativity, and it is not just science fiction. It is a confirmed reality of our universe. The resolution lies in the fact that time is not a universal constant that ticks away the same for everyone, everywhere. Instead, it is a fluid, personal experience that depends entirely on your motion and your proximity to gravity. For the twin racing through space at an incredible speed, time literally slows down. This effect, called time dilation, is described by mathematical equations known as the Lorentz transformation. It tells us that as an object's velocity approaches the speed of light, its passage of time relative to a stationary observer shrinks towards zero. We do not just see this in thought experiments, we account for it every single day. The global positioning system satellites orbiting our planet experience time slightly faster than we do on the Earth's surface. This is for two reasons. First, they are moving at high speeds relative to us, which slows their time a little. But second, they are farther from Earth's gravitational pull, which speeds their time up. The gravitational effect is stronger, so overall, the satellite's clocks run faster by about 38 millionths of a second per day. If engineers did not constantly correct for this relativistic effect, your phone's GPS would be wrong by several miles within just a few hours. Our daily navigation depends on accepting that time is malleable. So, the paradox is resolved because the situation is not symmetrical. The traveling twin undergoes actual acceleration to reach those phenomenal speeds, and then to turn around and come home. The stay-at-home twin does not. This acceleration breaks the symmetry, making the traveler's experience of time genuinely different. As physicists like Brian Greene explain, the traveler's path through the four-dimensional fabric of space-time is simply shorter. They have experienced less time. This leads to an astonishing conclusion. Time travel into the future is not only possible, it is inevitable under these conditions. You are doing a very tiny version of it right now, simply by walking upstairs, where time runs infinitesimally faster than in your basement. If we could build a ship that could withstand the acceleration to near light speeds, a crew could travel to the center of our galaxy and back, a journey of 50,000 light years. For everyone on Earth, 50,000 years would have passed, but for the astronauts, perhaps only 20 or 30 years would have gone by. They would return to a planet utterly transformed, effectively leaping tens of thousands of years into the future. This shatters our intuitive, linear perception of time, revealing it as a dimension that can be stretched and compressed. But this fluidity of time is only the beginning. What if we could manipulate it so drastically that we could send a message to our own past? Such an idea leads to a paradox so confounding it has troubled physicists for generations. That fluidity of time reveals a dizzying possibility. What if you could travel back and meet your own grandfather before he had any children? Driven by some unknown motive, you intervene in a way that prevents him from ever meeting your grandmother. If you succeed, your own parents would never be born. And if they were never born, you could never exist to travel back in time in the first place. So who stopped the meeting? This is the grandfather paradox, the ultimate logical trap for time travel into the past. It is not just a plot device for science fiction stories. It is a serious question about the fundamental rules of cause and effect that govern our universe. If the past can be changed, then the very act of changing it could erase the reason for the change, creating a loop of pure contradiction. How could reality possibly handle such a violation of its own logic? Some physicists, like Igor Novikov, proposed a fascinating solution. The Novikov self-consistency principle asserts that the past is already written and cannot be altered. Any actions a time traveler attempts in the past were always a part of that history. You might think you are going back to change something, but your presence and everything you do there is already factored in. Perhaps your attempt to interfere is what accidentally causes your grandparents to meet in the first place. In this view, the timeline is a single, unchangeable story. Your free will to change the past is an illusion. The universe would conspire through seemingly random events to prevent any paradox from ever occurring. A gun jam would stop you from firing. A sudden slip on a banana peel would make you miss your crucial intervention. The past protects itself, but what if the universe does not prevent a paradox but instead branches away from it? This is the many worlds interpretation applied to time travel. With every decision, every random quantum event, reality splits into a near infinite number of parallel timelines. In this multiverse, traveling to the past does not mean going back into your own history. You are simply crossing over into a different, parallel universe that is nearly identical to your past. In that new branch, your actions can change everything. You could prevent that version of your grandfather from having children, and it would have no effect on you because you originated from a separate timeline. You would not vanish, you would just be a stranger from another world, forever stranded in a history that is not your own. This idea offers a way out of the paradox, but it comes at a cost. You could never truly return to the home you remember, because your original timeline would remain untouched and inaccessible. Theoretical mechanisms for such journeys are just as bizarre as the paradoxes they create. Physicist Kip Thorne and others have explored the possibility of wormholes, hypothetical tunnels through the fabric of space-time. If you could stabilize a wormhole and move one end at near light speed, time dilation would cause that end to age much slower than the stationary end. Stepping through would be like stepping into the past. These pathways are described in Einstein's equations as closed time-like curves, but the quantum world seems to forbid them. The prevailing theory suggests that the energy required to hold a wormhole open would be so immense and unstable that any attempt to pass through would trigger a catastrophic feedback loop of radiation, destroying the tunnel instantly. The universe appears to have built-in safeguards against paradoxes. So where does this leave our understanding of cause and effect? The grandfather paradox forces us to confront whether our lives are governed by a fixed destiny or if every choice truly creates a new world. It challenges the very notion of free will, suggesting that either our actions are predetermined or our reality is just one thread in an infinite tapestry of possibilities. This enigma pulls us toward the quantum realm, where particles routinely defy classical logic, existing in multiple states and places at once, hinting that the rules of reality might be far more flexible than we ever dreamed. The quantum realm's defiance of logic finds its most famous symbol in a sealed box. Erwin Schrödinger, deeply troubled by the implications of quantum theory, devised a thought experiment not to celebrate its strangeness, but to expose what he saw as its absurdity. He imagined a cat placed in a steel chamber alongside a tiny, radioactive atom. If the atom decays, it triggers a mechanism that releases a deadly poison. According to the rules of quantum mechanics, the radioactive atom exists in a superposition. It is both decayed and not decayed until the very moment it is observed. Therefore, Schrödinger argued, the cat must also be both alive and dead, a grotesque mixture of states until someone opens the box and looks inside. This was his way of asking, at what point does this quantum blurriness resolve into the definite world we experience? The cat paradox pushes the observer effect to its most unsettling limit, forcing us to confront the bizarre consequences of superposition. This is the idea that a particle, or in this terrifying thought experiment, a living creature, does not have a single reality until it is measured. It occupies all possible configurations simultaneously. So, is the cat truly suspended between life and death, or is our understanding of reality fundamentally incomplete? Many physicists believe the resolution lies in a process called quantum decoherence. The cat is not isolated. It is constantly interacting with its environment. The air molecules in the box, the dust particles, even the temperature are all making countless tiny observations. This constant interaction with the outside world causes the fragile superposition to collapse almost instantly. The system chooses a state, becoming definitively either a living cat or a deceased one, long before a human ever lifts the lid. The blurriness resolves itself without a conscious observer. This explanation anchors reality in the physical world, but another interpretation offers an even more radical vision. Hugh Everett proposed the many worlds interpretation, which takes superposition at its word. In this view, the moment the radioactive atom faces its quantum choice, the universe itself splits. In one branch of reality, the atom decayed and the cat is dead. In another, equally real branch, the atom did not decay and the cat is alive and well. There is no single collapse. Instead, every possible outcome physically happens, each in its own newly created universe. The conscious observer who opens the box simply becomes part of one of those branches, completely unaware of the other version of themselves who saw the opposite result. This leads to a profound question about our own identity. Are you a single, continuous consciousness, or are you constantly branching into countless other versions of yourself with every decision and every quantum event? What does it mean to be you if another you exists in a parallel world where you made a different choice this morning? The implications ripple outward, challenging the very nature of existence. If every possibility is realized somewhere, then reality is a tapestry of infinite parallel timelines. This quantum conundrum, born from a cat in a box, pushes our curiosity toward the most destructive places in the cosmos, where information itself seems to vanish forever. But this quantum blurriness, where every possibility seems to exist, confronts its ultimate test at the edge of the most destructive objects in the cosmos. A black hole's event horizon is a point of no return. Any information, whether from a star, a book, or a living creature, that crosses this boundary is thought to be lost forever, crushed into a single point of infinite density. Yet this idea creates a fundamental crisis known as the information paradox. Quantum mechanics insists that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. If you burn a book, the information in its letters is not gone. It is merely converted into the precise arrangement of smoke particles and heat. In theory, with a perfect understanding of physics, you could reverse the process and reconstruct every word. But a black hole seems to break this sacred rule. Information goes in and simply vanishes. Stephen Hawking's revolutionary work showed that black holes are not completely black. They slowly leak radiation and evaporate over astronomical timescales. But this Hawking radiation, he initially argued, is random and thermal. It carries no information about what fell in. So when the black hole finally evaporates completely, all the information about the stars and planets it consumed is erased from the universe. This presents a stark choice. Either our understanding of quantum mechanics is wrong, or our understanding of gravity is wrong. This paradox forced physics to evolve. Hawking himself eventually changed his mind, conceding that information must be preserved. But how? The answer may be one of the most profound ideas in modern physics, the holographic principle. It proposes that all the information describing the three-dimensional volume of a black hole is not stored inside it. Instead, it is encoded like a hologram on its two-dimensional surface, the event horizon. Imagine watching a movie on a flat screen. The image appears to have depth, but all the data is stored in the pixels on the flat surface. In the same way, our perception of a three-dimensional reality falling into a black hole might be a projection from a two-dimensional surface of information. This leads to a startling possibility. Our entire universe, with its galaxies, stars, and planets, might not be fundamentally three-dimensional. It could be a holographic projection from a two-dimensional shell at the edge of the cosmos. We would be living inside a hologram, but if information is preserved on the surface, how does it escape? This question ignited the firewall paradox. Does the event horizon have a searing wall of energy that incinerates anything falling through? Most physicists, like Leonard Susskind, argue against this. They believe the information is transferred, scrambled but preserved, in the Hawking radiation through a complex process involving quantum entanglement. This is explored through frameworks like the AD/S/CFT correspondence, a theoretical tool that suggests a universe with gravity can be perfectly described by a quantum field theory on its boundary without gravity. The information is not lost, it is translated into a different, incredibly complex language. This resolution to the paradox suggests that space-time itself may be emergent, not fundamental. It arises from a deeper, more basic layer of quantum information. The crisis of lost data in black holes forces us to question the very nature of our reality. Are the three dimensions we move through an illusion? Is the cosmos a vast cosmic projection? This information crisis pulls us inevitably toward the ultimate question, the origin of everything, where the rules of physics as we know them simply break down. The idea that our universe is a cosmic projection is staggering, but the true mystery begins with the numbers themselves. The fundamental constants of nature seem almost too perfect. The strength of gravity, the force that binds atoms, the mass of an electron, each of these values is set with a precision that defies belief. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself moments after the Big Bang. If it were slightly weaker, galaxies and stars could never have coalesced from the primordial gas. There would be no planets, no chemistry, and certainly no life. The same is true for the other constants. A tiny change in the strength of the nuclear force, and stars would be unable to forge the carbon that is essential for our existence. It appears the universe was tailor-made for us. This is the fine-tuning paradox, and it presents a monumental question. Is this cosmic coincidence evidence of deliberate design, or are we the beneficiaries of unimaginably good luck? Physicist Martin Rees has famously highlighted the sheer unlikelihood of it all, identifying 6 of these numbers as crucial for our cosmic address. The odds of them all aligning so perfectly in a single universe seem infinitesimally small. This puzzle leads directly to the anthropic principle, a simple yet profound idea. The universe must be compatible with our existence as conscious observers because we are here to observe it. In a universe not fine-tuned for life, no one would be around to wonder why. But this feels like a tautology, an answer that simply restates the question. It does not explain why the constants are so perfectly set. To resolve this, some scientists propose a radical solution, the multiverse. Imagine not one universe, but a vast, perhaps infinite, collection of them, each with its own random set of physical laws and constants. In most of these universes, the numbers are all wrong. Stars flicker out instantly, atoms never form, and reality is a barren, chaotic void. But in a vanishingly rare few, like our own, the numbers line up just right. We do not live in a special universe, we simply live in one of the few that can support life. This is cosmic natural selection on the grandest possible scale. Our presence here is not a miracle, but a statistical inevitability given enough rolls of the dice. This framework, however, sparks intense debate. Does the multiverse explain fine-tuning, or does it merely push the question back a step? Where did the multiverse itself, with its capacity to generate universes, come from? The fine-tuning paradox forces us to confront our deepest questions about meaning. Does a universe born from a random draw in a cosmic lottery feel less significant than one crafted by a creator? Or is the sheer, breathtaking improbability of our existence, against all conceivable odds, the most profound meaning of all? This search for an answer pulls us back to the very beginning, to the moment of creation itself, where another paradox awaits. The search for cosmic meaning brings us to a truly unsettling possibility. Ludwig Boltzmann, a physicist grappling with the nature of disorder, proposed a concept so strange it bears his name. The universe, according to thermodynamics, is constantly sliding toward a state of maximum entropy, which is a fancy word for ultimate disorder and chaos. Think of a hot cup of coffee left on a table. It does not get hotter, it cools down, its heat dissipating into the room, increasing the overall disorder. This is the arrow of time, the reason we remember the past but not the future. The puzzle Boltzmann tried to solve was why we see so much order, like galaxies and planets and ourselves, if the universe is supposed to be descending into chaos. His radical suggestion was that our entire ordered cosmos is nothing but a rare, random fluctuation. In a vast and eternal sea of maximum disorder, a small pocket of order can spontaneously appear just by sheer chance. This leads to the ultimate solipsistic nightmare, the Boltzmann brain. It is far more probable for a single, self-aware brain to randomly fluctuate into existence, complete with false memories of a past and a vivid hallucination of a universe, than it is for an entire, ordered universe like ours to form. The math, in a sense, favors the lone, disembodied mind over the complex reality we take for granted. So, are you a Boltzmann brain? Is everything you see, feel, and remember merely an elaborate illusion concocted by a consciousness that formed from the void just a moment ago? This paradox strikes at the foundation of everything we consider knowledge. How could you ever trust your senses, your memories, or the laws of physics if they might be a temporary and improbable glitch? Modern cosmology offers a potential escape route through the theory of cosmic inflation. Physicists like Sean Carroll explain that our universe did not begin in a state of high entropy. The Big Bang was a moment of incredibly low entropy, a state of perfect order that set the arrow of time in motion and allowed for the structured cosmos we see today. Inflation, a period of hyper-fast expansion in the universe's first moments, provides a mechanism for this initial low-entropy condition. In this view, our universe is not a random fluke in an old, chaotic cosmos, but a natural product of a specific beginning. The probability of a Boltzmann brain forming is then vastly overshadowed by the reality of our cosmic history. Yet the idea lingers, a ghost in the machine of reality. It forces us to ask what is more real, the consistent external world we all seem to share, or the private theater of our own consciousness. This eerie thought experiment connects directly to modern questions about simulated realities. If a universe can be hallucinated by a single brain, could we all be living inside an advanced computational simulation? The Boltzmann brain pushes us to the precipice, making us question not just the cosmos, but the very nature of the self that observes it. That profound uncertainty about the self and reality finds a modern echo in a startling question. Are we living inside a computer? The simulation paradox suggests that a future civilization, with technology far beyond our own, might choose to run incredibly detailed simulations of conscious beings, perhaps to study history or for entertainment. Philosopher Nick Bostrom formalized this idea, arguing that if such simulations are possible, then the number of simulated minds would quickly and vastly outnumber the minds in the one base reality. Statistically speaking, if there are billions of simulated experiences for every one authentic one, the odds are overwhelming that you and I are not the original, but the simulation. This is why figures like Elon Musk have stated they find the argument compelling, suggesting the chance we are in base reality is just 1 in billions. The logic is as simple as it is unsettling. But is such a feat even possible? The limits might be found in the quantum world. To simulate every particle in a universe with perfect fidelity would require unimaginable computational power, perhaps more energy and memory than the base universe itself contains. Some physicists argue that the inherent randomness and blurriness of quantum mechanics could be a fundamental block, a feature of reality that cannot be perfectly computed, acting as a firewall against total simulation. Yet, what if the simulation does not need to be perfect? What if it only needs to be good enough to fool its inhabitants, rendering fine details only when we look closely, much like a video game loads a new area as a player approaches? This line of thinking leads to profound ethical questions. If our world is a simulation, do our choices, our loves, and our struggles have any meaning? Or are we merely characters in an elaborate story, our fates pre-written by lines of code? The answer might be that meaning is not something granted from the outside, but something we create from within. Even if this is a simulation, the pain you feel is real to you. The joy you experience is no less vivid. Our consciousness, whether born of biology or bits, is the only reality we have ever known. So how could we ever test this hypothesis? Some scientists have proposed looking for glitches or shortcuts in the laws of physics, tiny errors in the programming of our universe. Perhaps we might find evidence of a limited resolution to space-time, a pixelation at the smallest possible scale. The simulation paradox ultimately challenges our deepest assumptions about authenticity. It forces us to ask what makes a life real. Is it the substance we are made of, or the experiences we accumulate? If we one day create such simulations ourselves, we would become the gods we once wondered about, closing a cosmic loop that reframes existence itself. This digital hall of mirrors pulls our gaze from the nature of reality to the very tools we use to perceive it, where light itself holds a final, beautiful contradiction. That question of authenticity, whether we are made of flesh or code, leads to an even deeper puzzle about our own physical existence. A legendary ship once sailed by the hero Theseus rests in a harbor. Over centuries, its wooden planks rot and are replaced one by one until not a single original piece remains. Is the vessel sitting in the dock still the Ship of Theseus? Now gather all the old, discarded planks and use them to reconstruct the ship perfectly. Which one is the true original? This ancient thought experiment is the paradox of Theseus, and it cuts to the heart of what it means for anything to persist through time. Your own body is a living example. Nearly every cell you had 7 years ago has died and been replaced. The atoms that constitute you today are almost entirely different from the atoms that made you a decade ago. They have been recycled from the food you eat and the air you breathe, many having once been part of other people, ancient stars, or long-extinct creatures. So, in what tangible sense are you still the same person? Philosopher Derek Parfit used this paradox to explore psychological continuity, suggesting that what matters is not a mysterious, unchanging self, but the chain of connected memories, personality, and experiences that link you to your past. You are a narrative, not a statue. This concept explodes in scale when we look at the cosmos. A star like our sun is not a static, solid object. It is a furious, dynamic furnace, constantly fusing hydrogen into helium in its core and shedding particles into space as solar wind. Over its multi-billion-year life, its entire composition changes. The star you see tonight is materially different from the one that existed 1 million years ago. Is it the same star? Galaxies are even more dramatic. They collide, merge, and are reborn, their stars scattered and reformed. The Milky Way is continuously consuming smaller galaxies and being reshaped by the process. When two galaxies become one, which identity survives? The answer from modern physics is both unsettling and beautiful. Quantum field theory tells us that what we call a particle is not a tiny, permanent billiard ball. An electron is more accurately a knot of energy in a field, constantly interacting with its environment by exchanging virtual particles. It is a process, not an object. Its identity is defined by its relationships and properties, not by a core, unchanging substance. At the most fundamental level, everything in the universe is in a state of flux. There is no permanent essence. An object, a planet, or a person is more like a whirlpool in a river. The water molecules are always new, yet the pattern persists. The whirlpool's identity comes from its structure and its dynamic form, not from the specific water flowing through it. So, are you the same person you were a decade ago? The answer may be no in a material sense, and yes in a continuous, evolving pattern of information and consciousness. This realization that nothing is static pulls our gaze outward to the grandest scales of all, where the very concepts of something and nothing begin to blur into an infinite void. That profound darkness above us holds a secret contradiction. If the universe is truly infinite and filled with an endless number of stars, then every single line of sight in the night sky should eventually land on a star's surface. The entire celestial dome should be a solid, blinding sheet of light, as bright as the surface of the sun. Yet when we look up, we see blackness, punctuated only by tiny, isolated points of brilliance. This is Olbers Paradox, named for the German astronomer Heinrich Olbers, who framed it in the 19th century. It is a cosmic riddle that seems simple, but its answer unravels the very nature of reality. For a long time, scientists assumed a static, eternal cosmos, one that had always existed and would always remain the same. In such a universe, the darkness of night is impossible. The only way to resolve the paradox is to realize that our universe is neither static nor eternal. The first key is the finite speed of light. Light from the most distant stars takes time to reach us, and the universe is simply not old enough for light from every possible star to have arrived. We are surrounded by a cosmic horizon, a limit to how far we can see. Beyond that horizon, there are countless galaxies whose light has been traveling for billions of years, but has not had enough time since the beginning of everything to finally reach our eyes. The second, even more critical piece is the expansion of the universe itself. As space stretches, the light traveling through it also stretches, shifting its color toward the red end of the spectrum. This redshift saps the light's energy, making distant stars and galaxies dimmer than they otherwise would be. For the most ancient and faraway objects, this stretching is so extreme that their light is shifted entirely out of the visible spectrum and into the invisible infrared, effectively fading them from view. As the astronomer Edward Harrison eloquently explained, the darkness of the night sky is not an empty void. It is a direct observation of the universe's dynamic history. That pervasive blackness is the final, redshifted glow of the Big Bang's initial fireball, stretched and cooled over 13.8 billion years into the faint cosmic microwave background that permeates all of space. This paradox, therefore, is not a flaw in our reasoning but a profound clue. The dark sky is evidence that the cosmos had a beginning. It tells us the universe is evolving, expanding, and has a finite age. It forces us to confront the ultimate question of what, if anything, came before that first moment. Does this cosmic birth imply a final end? The answer to a simple question about the night's darkness pulls us toward the ultimate mysteries of existence and non-existence. That profound darkness is a testament to a universe with a beginning, and every beginning implies a possible end. Our cosmos is sliding toward a state of absolute equilibrium, a final, frozen state known as heat death. In this distant future, trillions of years from now, the last stars will have burned out, black holes will have evaporated, and all matter will have decayed into a thin, lukewarm sea of particles spread evenly across an ever-expanding void. There will be no more hot spots or cold spots, no flows of energy, and therefore no more work that can be done. Every process that defines existence, from nuclear fusion in stars to the firing of a neuron, will have ground to a permanent halt. The universe will be still, a fossil of its former self. This thermodynamic end presents a deep paradox. We perceive time as flowing from past to future, an arrow defined by increasing disorder or entropy. But if the universe reaches a state of maximum entropy where nothing ever changes again, what happens to time itself? If time requires change to be measured, does time simply stop? The very concept of an end becomes meaningless because there is no before or after in a realm of eternal sameness. This bleak forecast is not the final word for some physicists. Roger Penrose, for instance, proposes a breathtakingly beautiful alternative called conformal cyclic cosmology. He suggests that our universe's heat-death is not the true end, but rather a transition. In this state of infinite expansion and ultimate emptiness, the universe loses all sense of scale. A single, lonely photon traveling through the void would experience the entire cosmos as its own size. In this strange, scaled-less state, the end of our universe becomes indistinguishable from the Big Bang of a new one. The heat-death is reborn as a new fiery genesis in an endless cycle of eons. This idea offers a profound shift in perspective. It suggests that the cosmos is not a one-time event with a single, tragic conclusion, but part of an infinite, repeating loop. The death of one reality is the birth of the next, with information potentially being translated from one eon to another in ways we do not yet understand. This cyclical vision forces us to confront the philosophical heart of the paradox. Is meaning derived solely from impermanence? Does the fact that stars die and civilizations fade make our brief, brilliant moment more precious? Or could there be a different kind of meaning in an eternal cycle, where every story in some form is told again? The heat-death paradox pulls us from the edge of absolute nothingness toward the possibility of infinite rebirth, a cosmic phoenix rising from the ashes of its own expiration. A universe reborn from its own ashes is a cyclical mystery, but another paradox traps time in a perfect, mind-bending loop of its own. A time traveler, a passionate admirer of Shakespeare, journeys back to Elizabethan England with a complete collection of the Bard's plays. He hands the texts to a young, struggling William Shakespeare, who simply copies them out and claims them as his own. The plays are performed, they become legendary, and they are passed down through the centuries until our time traveler discovers them, meticulously collects them into a volume, and takes them back to the past. So, who actually wrote Hamlet? The information, the plays themselves, have no true origin. They were never created, they simply always existed, trapped in an infinite cycle where the effect is its own cause. This is the Bootstrap Paradox, a terrifying riddle of causality without a beginning. It asks a profoundly disturbing question. Can something come from nothing, not in a cosmic sense, but in the sense of an idea or an object that has no point of invention? In physics, this is not just a story. It relates to the theoretical closed time-like curves we encountered with wormholes, paths through space-time that loop back on themselves. If you could travel along such a curve, you could, in principle, become the source of your own existence. The laws of physics, as we currently understand them, do not explicitly forbid this. They just end up with equations that have no starting point. Philosophers have long grappled with a similar concept. Where do fundamental mathematical truths, like the rules of geometry, come from? They were not created, they were discovered. They seem to be self-existent, requiring no creator or prior cause. They just are. The Bootstrap Paradox applies this same logic to a physical object or piece of information, forcing it into a loop where it bootstraps itself into reality. To test the plausibility of such a reality, physicists like David Deutsch have explored how these loops might function using the principles of quantum computing. In a quantum system, a particle can influence its own past state through the loop, creating a self-consistent, but origin-less, set of information. The calculations show that the universe would likely enforce consistency. You could not create a contradiction, only a stable, if baffling, loop where the question of who wrote the plays becomes meaningless. The information was always there. This enigma forces us to reconsider the nature of invention and destiny. Every great discovery, every piece of art feels like a moment of creation. But what if these things are not created, but merely found, like artifacts from a future that already includes our act of finding them? Are we truly innovators, or are we just participants in a story that has already been written, a story with no author? This notion of an uncaused cause resonates with the greatest mystery of all, the spontaneous emergence of the entire universe from nothing, a void without a past where the ultimate bootstrap pulled reality into being. That same question of a story with no author applies to the very logic we use to understand the cosmos. A scientist stands in a forest, hoping to prove the statement that all ravens are black. Every black raven she observes seems to support her theory. Now consider a second statement, a logical mirror of the first. All non-black things are not ravens. A green apple is not black, and it is indeed not a raven. By confirming this second statement, the green apple also, logically, supports the idea that all ravens are black. This is the paradox of the ravens, a puzzle crafted by philosopher Karl Hempel, and it reveals a deep strangeness in how evidence works. We intuitively feel that a white shoe or a red barn has nothing to do with ravens, yet formal logic insists they provide a tiny shred of confirmation for the ornithological claim. The paradox highlights the challenge of inductive reasoning, the process of drawing general conclusions from specific observations. You can never prove a universal rule like all ravens are black by observation alone. You can only ever gather supporting evidence because a single, undiscovered white raven could always be lurking somewhere, waiting to shatter the entire theory. This is why philosopher Karl Popper argued that the true engine of science is not verification but falsification. A scientific theory is not one that can be proven true, but one that can be proven false. Good science makes bold, testable predictions that stick their necks out. The claim all ravens are black is scientific precisely because we can imagine finding a non-black raven and disproving it. Every failed attempt to falsify it strengthens our confidence, but it never grants absolute certainty. Now apply this to our cosmic solitude. Finding a single habitable, life-bearing planet like Earth seems to support the idea that life is common. But according to the Raven logic, this discovery also supports the opposite idea. If life is common, then finding a lifeless, barren world should be rare. So when we find a desolate Mars or a scorching Venus, these dead worlds, the green apples of the cosmos, paradoxically offer a tiny bit of confirmation that life is common elsewhere. This feels deeply counterintuitive. It shows us that absence of evidence is not evidence of absence, a crucial principle in the search for extraterrestrial intelligence. Our telescopes have not yet found signs of other civilizations, but that does not mean they are not there. It only means we have not yet observed the specific evidence that would falsify our loneliness. We are like the scientist in the forest who has only examined a few trees, declaring the entire woods empty of a certain bird, when the creature might simply be hiding in the unexamined branches. This reasoning dilemma forces a profound humility. Our knowledge of the universe is built on a tiny, localized sample. We are drawing grand conclusions about the prevalence of life, the laws of physics, and the nature of reality from a single data point, our own existence. Does this undermine scientific certainty? It reframes it. Science does not deal in absolute truths, but in the best, most rigorously tested models that have, so far, resisted all our attempts to break them. This dance between confirmation and falsification echoes right back into the quantum realms, where the act of observation itself defines what is real, and the very particles we study refuse to be pinned down until we look. Our reliance on logic to understand the cosmos can lead us to conclusions that defy all physical intuition. A single, solid ball of gold can be mathematically divided into a finite number of pieces, and these pieces can then be simply rotated and reassembled to create two perfect, solid balls of gold, each identical to the original. This is the Banach-Tarski Paradox, a theorem in set theory that is rigorously true within the abstract world of mathematics. The trick lies in the nature of infinity. The pieces themselves are not solid chunks you could hold in your hand. They are infinitely complex, dust-like constructions, so jagged and fragmented that they cannot be assigned a coherent volume. These are called non-measurable sets. Their creation relies on a powerful and controversial mathematical tool called the axiom of choice, which allows us to select one item from each of an infinite number of sets, even without a defined rule. When you reassemble these infinitely complex, volumeless pieces, you are essentially creating volume out of nothing that our everyday physics recognizes. The paradox does not work in the real world with atoms and molecules, but it forces a profound question about the fundamental fabric of reality. Is the universe at its most basic level continuous and infinitely divisible, or is it made of discrete, indivisible pixels of space and time? If space-time is a smooth continuum, then the bizarre logic of Banach-Tarski might lurk in its deepest foundations. This is where the concept of quantum foam arises. At the unimaginably small Planck scale, a distance of 10 to the negative 35 meters, the smooth geometry of spacetime is thought to break down. It might become a seething, probabilistic froth, where tiny wormholes and baby universes continuously pop in and out of existence. In this realm, the very ideas of before and after, or here and there, become meaningless. As Stephen Hawking speculated, the singularities at the hearts of black holes, where density becomes infinite, might be described by such mathematical oddities, places where the normal rules of volume and dimension simply cease to apply. This paradox forces us to confront the unsettling power of infinity. It is not just a very large number, it is a concept that can shatter our classical understanding of the world. The sphere duplicated from a single sphere is not a magic trick. It is a glimpse into a deeper layer of mathematical truth, one that suggests our reality might be far stranger and more malleable than the solid, predictable world we experience. This abstract puzzle about the nature of space pulls our focus toward the very dimensions we inhabit, where another paradox suggests our universe might be a shadow of a far richer reality. That abstract puzzle of mathematical spheres finds its echo in a far more tangible problem, one you can feel with every step you take. To walk across a room, you must first reach the halfway point. But before you can get to that halfway mark, you have to cover half of that distance, and before that, half again, and so on forever. You are faced with an infinite number of these halfway points to cross before you ever arrive at your destination. How can you complete an infinite number of tasks in a finite amount of time? This is Zeno's Dichotomy paradox, an ancient Greek thought experiment that suggests motion itself is nothing but a grand illusion. If space is a smooth, continuous fabric that can be divided forever, then the simple act of moving from here to there becomes logically impossible. You are forever trapped in an infinite regress, always about to take the first step but never quite managing it. The classical solution to this riddle comes from calculus, the mathematics of continuous change. It shows us that an infinite series of ever smaller steps can indeed add up to a finite whole. The sequence of 1/2 plus 1/4 plus 1/8 and so on converges to exactly 1. The infinite number of tasks can be completed in a finite time because the time needed for each successive step shrinks along with the distance, eventually vanishing into insignificance. But does this mathematical trick truly resolve the paradox, or does it just cleverly sidestep it? Modern physics offers a far more radical answer. Perhaps space is not infinitely divisible. What if, like a digital image, reality has a fundamental resolution? This is where the Planck length comes in, a minuscule distance of about 1.6 times 10 to the negative 35 meters. At this scale, the very concept of distance and smooth space may break down into a grainy quantum foam. In theories like loop quantum gravity, pioneered by physicists like Carlo Rovelli, space is not a background stage. It is woven from a network of finite, discrete loops. Area and volume come in tiny, indivisible packets, much like how energy comes in quanta. You cannot have half a unit of space, just as you cannot have half a photon. In this pixelated cosmos, the infinite subdivision of Zeno's paradox hits a hard stop. There is a smallest possible distance. You move not by passing through an infinite number of points, but by jumping from one quantum of space to the next, like a pixel on a screen lighting up in a new location. This forces a profound reflection. Is the fluid motion we experience every day, a ball arcing through the air, a hand gracefully gesturing, just a convincing illusion generated by reality's incredibly fine grain? Are we, at the most fundamental level, watching a cosmic movie projected at an unimaginably high frame rate? This inquiry into the nature of motion and space pulls us directly into the quantum realm, where particles do not glide smoothly but make sudden, unpredictable jumps, existing in one state and then another without ever passing through the stages in between. That very idea of a pixelated reality where quantum jumps define motion leads to a phenomenon so counterintuitive it seems to defy common sense. A watched pot never boils, or so the old saying goes. In the quantum world, this is not just a folk wisdom, but a rigorous, demonstrable fact. Known as the quantum Zeno effect, it describes how the simple act of repeatedly observing an unstable system can prevent it from ever changing at all. Imagine a single radioactive atom poised on the edge of decay. Left unobserved, its wave function will gradually evolve, spreading out into a superposition of decayed and not decayed states until it eventually collapses into one outcome. But if you constantly measure it, asking over and over again, "Have you decayed yet?" you force its wave function to collapse back to its starting point each time. The system is perpetually reset, frozen in its initial state like a butterfly pinned in a display case. It is not that the atom is stubborn, it is that your relentless attention is actively holding it in place. Physicists George Sudarshan and Baidyanath Misra formally described this effect, naming it after the ancient Greek philosopher Zeno, whose paradoxes argued that motion was impossible. In modern laboratories, we see this not with pots of water, but with lasers and trapped ions. By shining a continuous, gentle laser light on a group of ions, scientists can effectively observe them without stopping their activity entirely. But if they pulse the laser rapidly, making a series of sharp, distinct measurements, they can freeze the ions' quantum states, preventing them from evolving or flipping as they naturally would. The more frequently you look, the less likely the system is to change. This raises a staggering philosophical question. If observation can halt the flow of quantum events, does that mean consciousness itself has the power to stop time, at least for the tiny systems we can measure? The line between being a passive observer and an active participant in the universe blurs into obscurity. Our attention is not a neutral spotlight, but a force that can shape reality on its most fundamental level. This effect suggests a cosmos where agency is woven into the fabric of existence, where our very gaze can impose a kind of stasis. It forces us to reconsider our role. Are we merely watching the cosmic story unfold, or are we, through the act of witnessing, also holding the narrative in place? This profound connection between mind and matter pulls us toward an even deeper mystery, where the universe itself might be a consequence of our own perception. We feel a genuine chill of fear when a movie monster lunges from the shadows, our hearts pounding with a terror that is utterly real. Yet, we know the monster is a fiction, a trick of light and sound. This is the paradox of fiction, a philosophical puzzle that asks how we can have such powerful, authentic emotional responses to things we consciously understand are not real. Philosopher Colin Radford pointed out the strange contradiction. We cry at a tragic play, we feel joy for a hero's victory, all while sitting safely in a seat, aware that none of it is actually happening. Our emotions seem to bypass our logical understanding, responding directly to the narrative as if it were truth. This paradox extends far beyond the theater, straight into our contemplation of the cosmos. We look at images from powerful telescopes, at the swirling colors of distant nebulae and the faint light of ancient galaxies, and we feel a profound sense of awe, a poignant melancholy for stars that died billions of years ago. We worry about the universe's eventual heat death, a cold, silent fate that will occur trillions of years in the future, long after every trace of humanity is gone. Why do we care if the universe is ultimately meaningless, or if it is a simulation or a grand illusion? Why should its fate stir any feeling in us at all? One explanation lies in the wiring of our own minds. We are creatures of empathy, our brains equipped with mirror neurons that fire not only when we perform an action, but when we see someone else perform that same action. This neural machinery allows us to feel the pain and joy of others, to step into their shoes. Perhaps this empathetic capacity does not shut off when the subject is not a person, but a planet, a star, or the cosmos itself. We project a narrative onto the universe, seeing its birth in the Big Bang, its vibrant life in the stars, and its eventual decline into darkness. We cannot help but empathize with this grand story, even if it is a story we are telling ourselves. Our cosmic curiosity, the deep, driving need to understand where we came from and where we are going, might be an evolutionary artifact. A brain that is curious, that seeks patterns and stories, is a brain that survives. It finds threats and opportunities. That same instinct, when turned upon the heavens, creates science and mythology alike. But what if it is more than just a useful glitch? What if our emotional engagement with the cosmos is not a one-way street? If our observation plays a role in shaping quantum reality, then our feelings of awe and wonder are not just passive responses. They are part of the relationship between the universe and the consciousness that has arisen within it. We are not just reading a story, we are participating in its writing. Our care for this cosmic narrative, real or simulated, might be the very thing that gives it meaning. In a universe devoid of any other obvious purpose, our capacity to feel awe, to care about the fate of distant galaxies, becomes a source of meaning in itself. The emotion is real, even if its object is ultimately mysterious. This deep connection between our inner psyche and the outer reality pulls us toward a final, fundamental tension, a paradox about the very substance from which everything is made. Our deep connection to the cosmos rests on a foundation of categories we believe to be solid. But what if the boundaries we rely on are illusions? A single grain of sand seems insignificant, but remove one from a heap and it remains a heap. Remove another and another and another. At what precise moment does the heap cease to exist? This is the Sorites Paradox, a riddle of vagueness that erodes the very idea of a clear line. It asks a deceptively simple question that has no simple answer, because there is no magical grain whose removal transforms a heap into a non-heap. This problem of vague boundaries is not just a philosophical word game. It strikes at the heart of how we classify everything in the universe. When does a collection of stars officially become a galaxy? At what point does a celestial body become a planet, rather than a dwarf planet or a large asteroid? Our dispute over Pluto's status was a perfect example of this cosmic vagueness in action. Even the edge of the universe is a fuzzy concept. Is it the farthest point we can see, the limit of expansion, or something else entirely? The philosopher Bertrand Russell argued that this vagueness is not a flaw in the world, but a limitation of our language. We impose sharp categories onto a reality that is fundamentally continuous and blurred. So are categories like planet or galaxy real things out there in the cosmos, or are they merely human constructs, useful fictions that help our minds organize a messy reality? One way to handle this ambiguity is through fuzzy logic, a system that deals in shades of gray rather than binary true or false. Instead of asking, is this a heap, fuzzy logic would assign a value like 0.8 heap, acknowledging its partial state. This mirrors the quantum world, where indeterminacy is a fundamental feature. An electron does not have a precise location until measured, existing in a cloud of probability. The boundary of an atom is not a sharp shell, but a fading haze where the probability of finding an electron gradually drops to near zero. The universe itself may be inherently vague at its most basic level. This forces a profound reflection on the limits of our knowledge in astronomy. How do we define a life form if we encounter something that is not carbon-based, or that exists as a planetary scale intelligence? Our current categories may be completely inadequate. The Sorites Paradox teaches us that the crisp definitions we crave are often a comfort, not a cosmic truth. Reality, from a grain of sand to a galaxy, exists on a smooth spectrum, and our attempts to draw lines are merely our way of navigating an infinitely complex and beautifully ambiguous cosmos. This fundamental vagueness in how we define things leads to a similarly strange problem, one that arises when we try to predict the future actions of an entity with a mind of its own. The crisp logic of prediction can collapse under the weight of its own certainty. A prisoner is sentenced to be hanged, but with a cruel twist. The execution will take place on a surprise day sometime the following week, from Monday through Friday. The prisoner, a keen logician, sits in their cell and begins to reason. It cannot be Friday, they conclude. If I reach Thursday evening alive, I will know the hanging must be Friday, and it would not be a surprise. Therefore, Friday is eliminated, but then they continue, it cannot be Thursday either. With Friday removed, if I reach Wednesday evening unhanged, I will know it must be Thursday, and thus it would also not be a surprise. One by one, the prisoner uses the same flawless logic to eliminate Thursday, Wednesday, Tuesday, and finally Monday. By the end of their reasoning, they have proven that a surprise hanging is logically impossible. They rest easy, confident in their safety, and then on Wednesday, the executioner arrives completely unexpectedly. The prisoner is shocked and the sentence is carried out. The surprise was genuine because their perfect prediction had been entirely wrong. This is the unexpected hanging paradox, and it reveals a fatal flaw in how we think about knowledge and the future. The paradox, analyzed by philosophers like Michael Scriven, is a vortex of self-reference. the prisoner's reasoning changes the very situation they are reasoning about. Their certainty about Friday eliminates Friday as a surprise day, which then changes the landscape for Thursday, and so on. The act of prediction itself invalidates the prediction. This is not just a brain teaser, it strikes at the heart of scientific forecasting. When we predict a catastrophic asteroid impact a century from now, does that very knowledge change the future? Could it spur the technological development to deflect the asteroid, thereby ensuring the prediction never comes true? The forecast creates a new reality where the forecast is wrong. This loops directly into game theory, where each player is constantly trying to anticipate the moves of others who are also anticipating their moves. It is an infinite regress of guesswork where perfect knowledge can be self-defeating. The prisoner's error was in believing they could outthink a system of which they were an integral part. Their logic was sound in a closed, abstract world, but it shattered when it collided with the messy, participatory nature of reality. We face this same dilemma when we contemplate the ultimate end of the universe. Our current models predict a cold, dark heat death. But could that very prediction, spread across a potentially infinite cosmos, inspire some future intelligence to find a way to reverse cosmic expansion, to cheat the thermodynamic end? The prediction of an end might, in some strange way, be the very thing that prevents it. This enigma connects back to the quantum world, where the act of measurement defines the outcome. Our expectations, our models, our very consciousness are not passive observers of a predetermined cosmic script. We are active participants, and our attempts to read the final page might just be writing it. That very act of prediction places us within a cosmic community, raising a profound ethical dilemma for any civilization that looks to the stars. A truly tolerant universe would seemingly welcome all forms of existence, yet it must also contend with those who are utterly intolerant, whose sole purpose is to dominate or destroy all others. This is the paradox of tolerance, a concept by philosopher Karl Popper, and it scales from human society to a galactic scale. If the cosmos tolerates a civilization that annihilates others, then tolerance itself becomes extinct. But if it does not tolerate the intolerant, then it is no longer fully tolerant. This is not just a philosophical exercise, it is the terrifying logic behind the dark forest hypothesis. Imagine the cosmos as a vast, dark woodland. Every civilization is a hunter, hidden and silent, moving through the trees. The moment one reveals its location by shining a light or calling out, it risks being instantly eliminated by another hunter who cannot take the chance that the new arrival is friendly. In this grim view, the great silence is not a mystery, it is a survival strategy. The Fermi Paradox is answered with a chilling simplicity. They are silent because they are hiding. The late astronomer Carl Sagan, a profound advocate for cosmic brotherhood and cooperation, understood this risk intimately. He passionately argued for sending messages of peace, yet he also cautioned that we might be like infants in a strange and unresponsive room, naively shouting without understanding who or what might be listening. His hope for a benevolent universe was always tempered by the sobering possibility that the first contact might not be a handshake, but a declaration of war. This forces us to ask whether the universe itself has built-in checks and balances. Perhaps the sheer distances between stars are a natural barrier, a quarantine that protects fledgling species until they are mature enough to handle the immense power of interstellar travel. Or maybe the great filter is an ethical one, a test that civilizations must pass, moving beyond self-destruction and aggression to earn a place in the cosmic conversation. As we stand on the threshold of becoming a spacefaring species, this paradox becomes our own. How do we balance our innate curiosity and desire for connection with the primal need for self-preservation? Do we continue to listen quietly, or do we take the risk and broadcast our existence to the galaxy, hoping to find friends but potentially inviting our own end? This moral quandary about how to behave in a potentially crowded but silent cosmos pulls our focus from external threats to an internal conflict, where the very logic we use to understand right and wrong can turn in on itself. A student stands before a judge suing their teacher for failing to impart a single lesson. The student argues that if the case is successful, the teacher must pay a fine. Yet, if the student wins the case, they have successfully proven they learned enough from the teacher to build a coherent legal argument, thereby demonstrating that the education was in fact effective. This is the paradox of the court, a 2,000-year-old puzzle that reveals the maddening elusiveness of knowledge itself. How can you prove you know nothing when the act of proving it requires knowledge? This ancient riddle echoes powerfully in our modern exploration of the cosmos. Our quest to understand the universe is perpetually shadowed by the question of what we cannot or may never understand. The Dunning-Kruger effect, a cognitive bias, shows that those with the least knowledge often overestimate their competence, while true experts are acutely aware of the vastness of their own ignorance. This is the very essence of scientific progress. The more we learn about dark energy, quantum fields, or the origin of the cosmos, the more we uncover the sheer depth of what we do not know. It is a humbling, expanding frontier of ignorance. The philosopher Socrates famously declared that true wisdom lies in knowing that you know nothing. This is not a statement of despair, but a starting point for genuine discovery. It forces us to ask whether any intelligent being, no matter how advanced, could ever overcome this fundamental barrier. Would a civilization 1,000,000 years older than ours, capable of engineering stars, still grapple with questions about the nature of consciousness or what, if anything, preceded the Big Bang? Or would they too find that every answered question simply reveals a dozen more profound mysteries lurking in the dark? Perhaps the universe is structured in such a way that some truths are permanently veiled, hidden behind event horizons of knowledge that no amount of intelligence can cross. This inquiry into the very nature of ignorance pulls us toward the final, fundamental paradoxes, where the universe confronts us with the ultimate limits of logic and the terrifying possibility of true nothingness. That very logic of prediction and surprise finds a strange echo in a simple question of birthdays. In a room of just 23 people, the chance that 2 of them share the same birthday is about 50%. This is the birthday paradox, and it feels completely wrong to our intuition. We tend to think of matching our own specific birthday, which in a small group is indeed unlikely. But the paradox counts every possible pair. With 23 people, you can form 253 unique pairs. That is 253 opportunities for a match, and that is enough to make the probability flip from unlikely to more likely than not. This counterintuitive result is a powerful lesson in probability. Small samples can produce surprising coincidences far more often than we expect. Now, expand this idea to the cosmic scale. The universe contains hundreds of billions of galaxies, each with hundreds of billions of stars, and a significant fraction of those stars likely host planets. The number of potential sites for life is not just large, it is astronomically vast, creating an almost infinite number of cosmic pairs where life could arise. From this statistical viewpoint, the emergence of life on Earth begins to look less like a miracle and more like a near certainty. This is the heart of the mediocrity principle in astrobiology, a guiding assumption that there is nothing inherently special about our position in the universe. Our planet, our star, and our galaxy are probably typical, not unique. If the laws of physics and chemistry are the same everywhere, then the processes that led to life here should be at work on countless other worlds. Experts like Frank Drake, who crafted his famous equation, understood that in such a vast cosmic room, coincidences like us are not just possible, they are statistically inevitable. This probability puzzle ties directly back to the fine-tuning paradox and the anthropic principle. We find ourselves in a universe suited for life, not necessarily because it was designed for us, but because in a near-infinite multiverse of possibilities, some universes will inevitably have the right numbers, and we can only exist in one of those. So, are we special, or are we just a statistical fluke? The answer may be both. We are a fluke in the sense that any specific instance of intelligent life is incredibly rare, but we are utterly ordinary in the sense that, given enough time and space, such flukes are bound to happen. This reshapes our understanding of cosmic evolution. Chance is not a minor player, it is the principal architect. The random collisions of molecules in a primordial ocean, the chaotic orbits of asteroids, the unpredictable paths of evolution, are all governed by probability on a grand scale. We are not the predetermined goal of the universe, but rather a beautiful, perhaps common, accident. This perspective does not diminish our significance, it reframes it. Our existence is a testament to the immense creative power of chance within a cosmos of limitless opportunity. Absolute freedom is a form of chaos. Without the constraint of physical laws, matter would never coalesce, stars would never ignite, and the universe would remain a formless, undifferentiated soup. Conversely, absolute order is a prison, a crystalline state of perfect, frozen symmetry where nothing new can ever emerge. The Liberty Paradox reveals that true potential exists only in the delicate balance between these two extremes. The fundamental constants of nature, the speed of light and the strength of gravity, are not limitations in the negative sense. They are the very constraints that make complexity possible. Imagine a game of chess with no rules. There would be no strategy, no beauty, no compelling narrative. It is the fixed rules of the board and the pieces that create an infinite space for creativity and surprise. Our cosmos operates on the same principle. The rigid laws of physics provide the stable stage upon which the unpredictable drama of emergence can unfold. This tension between determinism and free will is not just a human concern, it is woven into the fabric of reality. At the quantum level, the universe is fundamentally probabilistic. The outcome of a particle's decay is not preordained, it is a matter of chance. This inherent randomness at the foundation of everything injects a genuine openness into the cosmos. The future is not written, it is being written with every quantum event, every random collision, every choice made by a conscious mind. Philosopher Isaiah Berlin understood this dynamic well, arguing that some constraints are necessary for freedom itself. A river is most powerful when channeled by banks, just as a life finds its purpose within the boundaries of identity and morality. The universe's laws are its banks, guiding the flow of energy and matter toward ever more intricate forms. Without the constraint of gravity, there would be no planets to walk upon. Without the nuclear forces, there would be no atoms to build those planets. Does this mean the cosmos is a rigid, deterministic system or an open playground of possibility? The answer is both. The rules are fixed, but the game is one of near-infinite combinations. Every snowflake, every galaxy, every living creature is a testament to the boundless creativity that flourishes within these cosmic limits. This paradox forces us to see constraints not as walls, but as the very architecture of freedom, a necessary framework that allows for the spontaneous, beautiful, and utterly unexpected phenomenon of existence to arise from the void. That delicate balance between freedom and constraint brings us to the final, most profound mystery of all. Why does anything exist? the ultimate paradox is that there is a universe at all, rather than absolute and total nothingness. This question, which philosophers like Martin Heidegger considered fundamental, strikes at the very root of causation. We are used to asking what caused something, tracing a chain of events back in time. But if the universe truly began with the Big Bang, what caused the Big Bang itself? The very concept of cause and effect may break down at that singular point. One compelling answer comes from the quantum realm. Even in what we might call empty space, there is a seething, energetic activity. Virtual particles spontaneously pop into existence, borrowing energy from the void for an unimaginably brief moment before annihilating each other and vanishing. This is not a theoretical fantasy. We observe its effects, such as the slight shift in the energy levels of atoms, known as the Casimir effect. In a sense, the quantum vacuum is not truly empty. It is a fertile ground, a bubbling cauldron of potential. Physicist Lawrence Krauss has argued that this means nothing is inherently unstable. Given the laws of quantum mechanics, a state of pure nothingness would be a fleeting anomaly, inevitably giving rise to particles, energy, and ultimately a cosmos. The question then shifts from why there is something to why are there laws of physics that allow something to come from nothing. Other theories seek to eliminate the need for a beginning entirely. James Hartle and Stephen Hawking proposed the no-boundary proposal. Imagine the beginning of the universe not as a sharp point of infinite density, but as a smooth, rounded curve like the North Pole of the Earth. When you ask what is north of the North Pole, the question becomes meaningless. In the same way, in this model, the concept of a time before the Big Bang is meaningless. The universe would simply be without a boundary or an edge in time. It requires no creator and no prior cause. It just is. This leads to a staggering possibility. Perhaps true nothingness, a complete and utter void with no laws, no space, and no time, is not even a coherent concept. Our minds struggle to conceive of it because it may be a logical impossibility. Existence in some form may be the only possible state. So, what are the implications of this final paradox? It suggests that the universe is not a contingent accident in a sea of non-existence. It may be a necessary, self-contained reality, emerging from its own inherent mathematical and physical logic. Our journey through these 25 cosmic paradoxes returns us to where we began, staring into the night sky, but with a transformed vision. We have seen how reality is shaped by our gaze, how time is a personal experience, and how our entire cosmos might be a holographic projection. These are not mere intellectual curiosities. They are the fundamental tensions that define existence, the beautiful contradictions that force our understanding to evolve. The universe is far stranger, more mysterious, and more magnificent than we ever dreamed. And the greatest wonder of all is that we are here, a part of it, able to ask these questions and feel the awe they inspire. These cosmic puzzles are not a modern invention. They are as old as human thought itself, stretching back to ancient Greece, where a philosopher named Zeno first argued that a swift runner like Achilles could never overtake a tortoise if it were given a head start. His paradoxes of motion exposed a deep crack in our understanding of continuity and infinity, a crack that would not be fully mended for over 2,000 years. Aristotle wrestled with these contradictions, setting the stage for a scientific tradition where discomfort is not a sign of failure, but a catalyst for discovery. Each era's paradoxes perfectly mirror its understanding of the cosmos. In the clockwork universe envisioned by Isaac Newton, where every action had an equal and opposite reaction, a new contradiction emerged. If the universe was eternal and static, why was the night sky dark? This was Olbers Paradox, a direct challenge to the Newtonian picture that would only find its resolution with the revolutionary discovery of an expanding universe. The great leaps in science are almost always preceded by a paradox that the old model cannot explain. Einstein's own journey to relativity began when he contemplated a simple yet profound contradiction. What would a light wave look like if you could race alongside it at the same speed? According to the physics of his day, the wave should appear frozen, a possibility the equations said was impossible. This paradox forced him to redefine the very concepts of space and time, leading to his theory of special relativity. Historians of science see this pattern clearly. Thomas Kuhn described these moments as paradigm shifts, where the accumulation of anomalies and paradoxes becomes so great that the entire framework of knowledge must be rebuilt. A paradox is an engine of progress. It is the universe's way of telling us that our current map of reality is incomplete. Today, we stand at a similar precipice. The glaring conflict between the cosmic scale laws of general relativity and the particle scale rules of quantum mechanics represents the greatest unsolved paradox in modern physics. Both theories are spectacularly successful in their own domains, yet they are fundamentally incompatible when describing the core of a black hole or the first moment of the Big Bang. This is not a minor technicality. It is a screaming contradiction that is driving physicists toward a theory of everything, a unified framework that would weave these two pillars of physics into a single, coherent tapestry. The 25 paradoxes we explore are not isolated curiosities. They are part of this grand, historical conversation. They are the vital signs of a living, breathing scientific endeavor, the growing pains of our expanding comprehension. The puzzles that keep cosmologists awake at night, from the holographic principle to the mystery of dark energy, are the direct descendants of Zeno's ancient riddles. They are the questions that will not let us rest, forcing us to look deeper and imagine a reality far stranger than we ever thought possible. Our journey through these 25 cosmic paradoxes reveals a universe that is fundamentally fluid, a reality where the simple act of looking can change the outcome and where time itself is a personal experience. We have encountered a cosmos that might be a holographic projection, a single thread in an infinite multiverse, or even a sophisticated simulation. The solid, predictable world we experience is an illusion, a comforting simplification of a far stranger and more magnificent truth. These paradoxes are not failures of our logic, but vital signposts pointing toward a deeper understanding. They teach us a profound humility, reminding us that our knowledge is always provisional, a tiny island in a vast ocean of the unknown. The true mark of wisdom is not having all the answers, but having the courage to embrace the questions. Our exploration leaves us with a renewed sense of wonder, a childlike awe for the beautiful, mysterious, and often contradictory cosmos we call home. As the great Carl Sagan once said, somewhere, something incredible is waiting to be known. Let that be our guiding star. The universe is an endless frontier of mystery, and our journey has only just begun. We would love to hear which paradox challenged your view of reality the most, so please share your thoughts in the comments below. If you are hungry for more journeys into the heart of cosmic mystery, be sure to subscribe. Now, more than ever, keep looking up at the stars with curiosity and awe.